But yeah, so once they meet these criteria, they swallow each other up. The masses combine, the momentum combine, and they live the remnant just lives happily ever after, doing whatever it was doing before. So, physics ignored. Yes, totally. Yes, this problem is a big one and needs to be solved in smaller steps that I have not done yet. But it's on the list. Did you have a question over here?
Oh, I was just idly thinking that physics actually would cause a delay between when they come together.
Exactly.
So you would actually get higher SNRs because they'd be merging at lower rates.
Yes, because it would shift everything down a little bit.
Merging at all, that's the issue.
Yeah, if they merge at all. Yeah. But there's other things we can't resolve, like gas effects and three-body scattering, and so those things could accelerate the merger. Yes, big mattress, dirty, yucky mattress. All right. All right. So back to still on mergers, but back to the fact that remember that some of these galaxies are in the environments of larger Milky Way galaxies. And if you include so this doesn't include those mergers. These are just mergers, only mergers that happen in dwarfs. So I want to highlight the fact that black hole mergers that are just in dwarf galaxies do happen and will be detectable and could be important for LISA, because even though most dwarf galaxies may not have black holes, there are many dwarf galaxies, more than massive galaxies. And so something I'm going to work on in the future is doing actual predictions of merger rates and seeing what the contribution from low mass galaxies and low mass black holes will be to LISA's signal.
Sorry, you'll probably get to this in a minute, but what's the typical escape speed from the center of these dwarf galaxies, or are you just from where the mergers occur?
Yeah,
Tens
small.
of kilometers per second.
Okay.
Yeah. Yeah. My PhD student at Vanderbilt, Glenna Dunn, is actually working on a project to figure out sort of in a post-processing way when black holes eject, different ejection models, what the difference is in occupation fraction and black hole masses. And it turns out that black holes actually, even though they are ejected, often refill a host halo. And so the occupation fraction may not be super different. But I don't have that talk right here. I can talk about it. I'm around today and tomorrow. We can talk about it more. Okay, so if you include the massive galaxies in the black hole mergers, this is a histogram of the mass ratio of black hole mergers. And you can see that there's a spread here, but there's actually a huge peak right there. And that's about 1 to 50 is actually the most common mass ratio for black hole mergers if I include all of the mergers in the simulation. What does that correspond to? It corresponds to this situation here, remember our HLX1 friend, where we have a dwarf galaxy coming into a Milky Way galaxy, and often that black hole does work its way to the center and merge with the supermassive black hole in the central Milky Way. That is pretty common, more common than mergers in dwarf galaxies. So in these types of galaxy environments, these lower mass galaxy environments where a Milky Way may be the largest one, this is the most common mass ratio of merger that we see. This is important for many reasons. One, that we expect to see it with LISA, but also this is actually very difficult to model numerically in terms of general relativity calculations. 1 to 1 to 1 to 10 mergers are very easy to model, and like 1 to 1,000 mergers are very easy to model. Not very easy, but doable. But in this sort of intermediate, this is called an intermediate mass ratio in spiral, it's actually very complicated computationally. And waveforms have not been produced for mass ratios of this type yet. We do have about 15 more years to do that before LISA launches and will detect such a thing. And so I am confident that this will be done. But what my results show is that this will be an important contribution to the LISA signal, and so it's something that we need to get onto. Yeah.
So is this an artifact of how you're doing the simulation, in the sense that if it was a full cosmological, then the high mass ratio ones won't emerge because they're going to see a bigger potential wall as soon as from not emerging. So they're going to be, so these two galaxies are going to merge. They don't have time for the black holes to merge. They see another potential, they get unbound, so they are going to go orbit around the new, more massive central black hole, and this is going to merge, so they're going to be all floating. And the fact that you're saying that this is the mass ratio is that you stop the simulation, it is only for the dwarf, that probably
This is a cosmological simulation.
But are you,
It is a full cosmological simulation. It's a zoom simulation, so it's not a large statistical sample of a uniform volume, but it is a cosmological simulation.
for the Milky Way?
Yes, for the Milky Ways. There's four cosmological Milky Ways.
I think the isolated dwarfs are also from a cosmological zoom.
The isolated dwarfs are also from cosmological zoom.
Cosmological.
They all are, yeah.
So when you have something larger than the Milky Way, these become MBHs. The dwarfs then stay the same size roughly, but the host galaxy becomes larger.
Yes, yes. So if they have something larger than the Milky Way, then they would, so EMRI, extreme mass ratio in spiral, versus IMRI, intermediate mass ratio in spiral. If anyone has a better idea for a name, let me know. Because I wish they sounded a little more different. So yes, the EMRI, the extreme one, is easier to model computationally and numerically. And if you had a larger host galaxy, then the mass ratio would be that sort of thing. So if this is, it's like a Milky Way type black hole where it's 10 to the 6, and then these guys coming in are 10 to the 5 or so, then you get this mass ratio, more or less. All right. Well, that brings us to my conclusions. So the main points that I want to make are that dwarf and wandering supermassive black holes can give us clues to the original seed mass because they don't accrete very much. So if we can observe either AGN or black holes in dwarfs, or these wandering ones in the halos of larger galaxies, which, given both are very hard to observe, but we do have candidates for both. So that can give us clues to the original seed mass because these black holes probably haven't accreted very much in their histories. Many black holes in dwarf galaxies are not central, and this seems to be due to dynamical perturbations from galaxy mergers, and the fact that dwarf galaxies don't have deep potential wells, don't have a lot of mass, and so dynamical friction timescales are long. Once this perturbation happens, they don't go back into the center. Due to this slow dynamical friction, galaxies can host multiple intermediate mass black holes, which is really cool, and it'd be neat if we could detect such a thing. I'm looking, if anyone finds anything, let me know. And very few MBH mergers in low mass galaxy environments are 1-to-1. 1-to-50 is the most common mass ratio, which is something that we need to do more calculations about in order to properly predict the LISA signal and understand it when it happens. Go LISA. Thank you.
Questions? Anna.
So I want to get back to Ali's point that these should be very massive perturbers to the stellar population in dwarf galaxies. So I was just wondering, since there are now so many surveys doing result kinematics of galaxies in general and dwarf galaxies, like do you have a sense like how much of a signal or what precision would be required in those measurements to see the effect of a black hole? And I think this might work even if it's slightly off center, not just in the center.
Yeah, that's a great point, and I don't have that because I think in our simulations the star particles are still massive enough that wouldn't give a realistic view of what the perturbations would really be, and so I don't think I have a direct model comparison of what the massive black hole and actual mass stars, what their kinematics would be. But I definitely have talked to observers and told them to look for weird, unexplainable perturbations in stellar kinematics. No one has come back to me with anything that seems to be black hole related, but how you would determine if it was black hole related versus any other thing is another
Well, what you can do is post-process. You can just put test particles in your galaxy and then see how they behave in the presence of these black particles.
Yes, maybe my next summer student will
Exactly.
do this. Great idea.
Morgan?
I'm really interested in this correlation you were talking about between mergers and the subsequent star formation and off-center lights, massive black holes. And so I'm wondering if all of we looked at like the cumulative distribution of star formation in these different dwarfs, and they followed these very different tracks from like early star formation to late star formation. So are all the ones that have off-center dwarfs among the late star forming population?
There's no trend.
Okay, so basically in some cases, the story that you showed us where there's sort of star formation late and there's an off-center black hole that's not then accreting holes. But, so I'm asking basically if the black hole is off-center because of a merger, is that often accompanied by star formation at that epoch? So can we ask if those two are correlated?
They are not correlated with the small sample that I have.
Okay.
They are not correlated. The ones that are central also have a wide variety of star formation histories from early to late.
Yeah.
Those are central black holes, and the ones that have off-center black holes also have a variety of histories. It would be cool if they were correlated, because then you could
Okay,
say
so
something,
the
but they're not.
complication, I guess, that I wasn't appreciating is that the dwarfs with central black holes also have that wide range.
They do.
So
They do. There's
that sort of
there's not a
anything.
central black hole quenching thing going on. I have looked
Okay.
for that.
Okay.
That is not happening. I mean, it also, they're not, because they're not accreting, you wouldn't necessarily expect
Right,
that.
right.
If there was an accretion event that I saw anywhere, then I would definitely expect that. But because they're not accreting, even when they are central, you wouldn't necessarily expect there to be a star formation consequence.
Victor?
Can you say a bit about the sensitivity of these conclusions to the formation mechanism? So, for example, if you form from POP3 seeds, which potentially form in slightly more gas-rich environments that might accrete a bit more early on, would things change at all?
Probably.
Sure.
Do you want more details? Probably.